In this video, we will be looking at section 1.1, which is functions and function notation. We're going to start with the definition of a function. A function is a rule for a relationship between an input, which is also known as an independent quantity, and an output or a dependent quantity, in which each input value uniquely determines one output value. The way we say that out loud is the output is a function of the input. Kind of the short way of saying this is each input has only one output. So if you give this function a value, it can only give you one value in return. So let's think of some real-world examples. At a vending machine, is the item code a function of the price? So what that's saying is, if I tell you what the price is, can you tell me which item code I'm going to press? Well, not necessarily. Maybe there are two items that are the same price. For example, maybe a Pop-Tart and a Honey Bun are both $1. So if I tell you that I'm going to buy something that's $1, do you know what I'm buying? Not necessarily. Let's try switching that around. Is the price a function of the item code? If I tell you the item code that I'm going to type in, are you going to be able to tell me the price of the object? Well, hopefully, yeah. Because in vending machines, when you type in a certain code, it tells you what price it's going to charge. Next up, is the temperature in degrees Celsius a function of the equivalent temperature in degrees Fahrenheit? So if I tell you the temperature in Fahrenheit, can you tell me the temperature in Celsius? Well, yeah, there's an equation for that. If we switch it around the other way, is the temperature in degrees Fahrenheit a function of the equivalent temperature in degrees Celsius? If I give you the temperature in Celsius, can you tell me the temperature in Fahrenheit? Well, yeah, you just use that formula the other way around. Because exactly one Fahrenheit temperature matches with one Celsius temperature. Let's move on to something that might feel a little bit more applicable. Is your letter grade in a class a function of the percentage grade you have? So if you know what percent you have in a class, do you know what letter grade you have? Usually, yeah. Because if you know you have, say, an 82 in a class, that's a B. If you know you have a 96, you have an A. Let's switch that around. Is the percentage grade you have a function of the letter grade you have? So if you know the letter grade, do you know what percentage you have? No. Because if you know you have a B, you could have an 86, an 84, an 82, an 89. You don't know. So that's what this idea of function is and how we can word it so that we know what's going on. So next up, we are going to talk about what a one-to-one function is. It's a relationship in which each input corresponds to one output, and every output corresponds to exactly one input. So it's like a function. Well, it is a function. It's a one-to-one function. But you can go the other way as well. Each output has only one input as well. So if we want to think of some real-world examples, we already talked about one. That was the temperature. We can go between degrees Fahrenheit and degrees Celsius because a degree Fahrenheit corresponds to only 1 degree Celsius, and vice versa. If you know the temperature in one, you can figure out the temperature in the other. We could go from inches to feet, and vice versa. So any of these measurements where we have some sort of calculation to convert. What about the length of fence you buy to the price? As long as you're getting just one type of fence, then it's going to be the same price for each foot or whatever. So if you know you're going to pay X amount, you can figure out how long the fence is. If you know how long the fence is, you're going to be able to figure out what the price is going to be. So this idea of one-to-one function is you can go back and forth and there's only one choice each way. Let's take a look at function notation. The notation f parentheses input equals output defines a function named f. So this letter out front is the name of the function. We read this out loud as f of input equals output. So for example, if we define the function capital D to be the number of days in a given month on a non-leap year, we're so not going there, then we say that D of June equals 30 because the function D is the number of days in a given month. So if we want to know the number of days in June, that's 30. We're going to take a look at some functions in the form of tables. We're going to determine which, if any, of these following tables define functions. And if it is a function, we want to figure out if it defines a one-to-one function. So let's start with table A. First off, is it a function? Does each input have only one choice for output? Well, let's check. An input of 3 gives us 8. An input of -1 gives us 6. 9 gives us 2. 8 gives us 6. 0 gives us 0. Sure, that one's a function, because each input has only one choice for what the output's going to be. Let's check to see if it's one-to-one. Does each output only have one input? An output of 8 gives us an input of 3. An output of 6 gives us -1. But wait a minute. There's another output of 6 here. If I know my output is 6, then either my input is -1 or 8. So this output 6 has two different inputs. That is not a one-to-one function. Because the output of 6 has two different inputs. Let's look at letter B. First off, is it a function? Looking at our inputs, I already see that we have 1 as an input twice, and it has two different outputs. If an input has two outputs, that means it is not a function. And if it's not a function, it can't be a one-to-one function, so we're done with that one. Letter C, is it a function? We have all different inputs. None of those repeat, so it is a function. Let's check to see if it's one-to-one. Does each output have only one input? Output of 2 goes to 1, 3 goes to 2, 4 goes to 3, 5 goes to 4, 6 goes to 5. Yeah, this one's a one-to-one function because each output has only one input. Let's try this last one. Is it a function? Looking at my inputs, they're all different. So yeah, that one's a function. To check to see if it's one-to-one, I need to check the outputs. I need to make sure each output has only one input. 2, 6, 4, 7, 1. Each of those are different, so they only have one input associated with them. So this one's one-to-one as well. So in this slide, we get to see the different ways this can happen. We could have a one-to-one function where each input has only one output and each output has only one input. We saw a function that was not one-to-one because of our output 6. It had two different inputs. That makes it not one-to-one. And then this table B here was not a function in the first place because we had the input 1 that had two different outputs. That makes it not a function. So here we have a table of a function, just kind of giving us some values. We're going to see if we can evaluate and solve using this table. So first off, we want to evaluate P of 3. So it looks like our top row is giving us R values, and our bottom row is giving us P of R values. So that means P is the name of our function, and it's taking R as an input. So if we want to evaluate P of 3, it's saying let R, our input, be 3. It's asking for the output. So if R equals 3, what is P of 3? It's going to be 7. In the second part, we want to solve P of R equals 2. What that's asking for is what R value makes this true. So I can go figure out where P of R is equal to 2, and then it looks like it happens right here. So what is the R value that makes that true? 0. So we say R equals 0 is the way we solve that. Let's try looking at some graphs. We want to determine if we can, we need to determine from the graph whether or not this represents a function. So which of the following graphs defines a function y equals f of x? So if x is our input and y is our output, do we have functions? And if it is a function, is it one-to-one? So let's start with graph A. Since x is the input, we want to check to see if each x has only one y value. Well, yeah, we don't have any repeated x values, so yeah, this one's a function. Let's check to see if it's one-to-one. So one-to-one means given an output, is there only one input for it? Well, let's take a look, say, right here at y equals 2. Y equals 2, since y is an output, I see 3 different x values or 3 inputs that give me 2 as an output. That means this is not one-to-one because we have an output with multiple inputs. Moving on to graph B, we want to check to see if that is a function, and if it is, if it's one-to-one. So checking if it's a function, do any of our x values repeat? Nope, so it's a function. To check to see if it's a one-to-one function, do any of our y values repeat? No, it doesn't look like it, so this one is not, or sorry, this one is one-to-one. Each input, x, has only one y value. Each output, y, has only one input, x. So this one is a function and a one-to-one function. Finally, we have graph C, which is a circle. First, we want to check if this is a function. Does each x value have only one y value? And that's a big old no. For example, if we look at, say here, -1. The x value, -1, has 2 different outputs. That means it is not a function. I'm hoping going through these you were reminded of a certain test that we can use on graphs. First up, we have the vertical line test. The vertical line test tells us whether or not something is a function. If no vertical line would cross the graph of a relation more than once, then the graph is a function. So you need to be able to drag a vertical line all the way across your graph. If it never intersects more than once, then you have a function. Once you know something's a function, you can use the horizontal line test. The horizontal line test is going to tell you whether or not the function is one-to-one. So if a relation has been determined to be a function, then if no horizontal line would cross the graph more than once, then the function is a one-to-one function. So if you already know it's a function, using the vertical line test, you can use the horizontal line test to check to see if it's one-to-one. And that's kind of what we did. You can see that graph A passes the vertical line test because any vertical line only ever intersects the graph once, but it fails the horizontal line test because this horizontal line here, y equals 2, intersects the graph more than once. So that makes it not one-to-one. Graph B passes both the vertical and the horizontal line test, so it is a one-to-one function. and graph C fails the vertical line test, which makes it not a function. So those two tests are going to tell you whether a graph represents a function, and if it is a function, whether or not it is a one-to-one function. Now we're going to take a look at a graph and see if we can evaluate a function and then solve an equation using it. So we're looking at this graph and we want to evaluate f of -1. So notice that the x is what came in parentheses after f, so that's going to be my input. So -1 is my x value. It's asking what is the y value if x is -1. So I find the point on my graph where x is -1. It's going to be right here. The y value there is 3. So that is equal to 3. Then we want to solve f of x equals 0. So it's saying when y equals 0, what is x? So when y is 0, we are on our x-axis. That actually happens in 1, 2, 3 places. At -2, 0, and +2. This one is a function. It does pass the vertical line test, but this here shows it is not a one-to-one function because the y value 0 gave us 3 different inputs that worked for it. Now let's see if we can work with functions algebraically. Given the function t of m equals m squared plus 3m, first we want to evaluate t of 4. So that means we're going to plug in 4 as our input m. That's going to give us 4 squared plus 3 times 4. That is 16 plus 12, which is 28. So t of 4 is equal to 28. For part B, we want to solve t of m equals -2. So I'm going to replace my t of m with a -2. That gives me -2 equals m squared plus 3m. This is a quadratic equation. We know that because our variable is squared. To solve quadratic equations, we have to get 0 on one side of the equation first. So I'm going to add 2 to both sides. That gives me 0 is equal to m squared plus 3m plus 2. At this point, we can use the quadratic formula or we can factor. Because it factors nicely, that's what I'm going to do. That gives me 0 is equal to m squared, or sorry, factoring. That gives me 2 sets of parentheses. M's out front. I need a +2 and a +1. So 0 is equal to m plus 2 times m plus 1. Since I have 2 things multiplied together, that gives me 0. One of them must be 0. If m plus 2 equals 0, then we get m equals -2. If m plus 1 equals 0, then m equals -1. We get 2 solutions that work, -2 and -1. Finally, we want to evaluate t of 3 minus t of -3. We're going to start by finding both t of 3 and t of -3. Oops. T of 3 just means plug in 3 for our input m, which is 3 squared plus 3 times 3. That is 9 plus 9, which is 18. T of -3 will be -3 squared plus 3 times -3. -3 squared is -3 times -3, which is a +9. And 3 times -3 is a -9. And 9 minus 9 is 0. So if I go ahead and plug in what I got for t of 3 and t of -3, I get 18 minus 0, which is 18. The last thing we're going to do in this section is look at some basic equations that I need you to be comfortable with. First up, we have the constant function f of x equals 2. I need you to be able to recognize constant functions in general. So f of x equals any number. It's just going to be a horizontal line. Next up, we have the identity function. This is also a linear function because it's a straight line. That's going to be f of x equals x. We have the absolute value function, f of x equals the absolute value of x. That's the v shape. We have our quadratic function, f of x equals x squared. That's a parabola. We get our cubic function, f of x equals x cubed. And then there's 4 more. We have the square root function, f of x equals the square root of x. Kind of this little swish up. The cube root function, f of x equals the cube root of x. Looks kind of like x cubed on its side. We have the reciprocal function, f of x equals 1 over x. This is also called the inverse function. And then we have reciprocal squared, f of x equals 1 over x squared. With these 9 basic toolkit functions, I need you to be able to understand the formula, the name, the graph, and the table of how these interact. So if I give you a table, you need to be able to tell me the name. If I give you a graph, you need to be able to tell me the formula. You need to be able to go from any one to a different form. If I give you a formula, you need to be able to give me the name. So make sure you are comfortable with these 9 functions. They are important. We will need them for the rest of class, and I need you to be able to identify these functions at the snap of a finger.